This is a very similar question to the previous one. Um, so question A, let's show beta and gamma satisfy certain equations. Pretty simple, right? So by the linearity assumption, ui can be written as yi minus alpha 0 minus beta 0 x1i minus gamma 0 x2i. Okay, and then covariance between y and x, excuse me, covariance between x1 and ui, which is assumed to be 0. Oh, here it should be u, of course. U should be covariance between x1i, comma, yi minus alpha 0 minus beta 0 x1i minus gamma 0 x2i. Okay, which is, if you expand, covariance x1i yi minus covariance x1i alpha minus beta 0 covariance x1i x1i minus gamma 0 covariance x12. Simply let's write this way. Okay, and we have done this several times. This is 0. This is variance. Okay, rewrite that. Covariance x1 y minus 0 minus beta 0 times variance of x1i minus gamma 0 covariance x1 x2, right? This is 0 because we started from something that equals to 0. We can do the same thing for, I'll do it here, covariance x2 and y in u. Then you will get, in the end, you can follow the same algebra, x2i minus beta 0 covariance x2i x1i minus gamma 0 variance x2i. Okay, and you know covariance is interchangeable. These two are the same thing. Covariance 1 2 is covariance 2 1. They are the same thing. So then we have covariance x1i yi equals beta 0 variance x1i plus gamma 0 covariance x1 x2. Second equation is beta 0 covariance x1 x2 plus gamma 0 variance x2. Right? We have two linear equations with the same parameter. In these equations, unknowns are the parameters, beta and gamma, and you should become familiar with the linear like matrix notation. Covariance x1i yi, covariance x2i yi equals the matrix beta 0 gamma 0, right? You know, variance x1, covariance x1 x2. Simply let me write just this way, right? So the first question, we proved this one. What I wanted to show you again here is I did not use the error terms mean. The error terms mean can be 0 or not, does not matter. Still, we can ignore that and we can identify beta 0 and gamma 0 if this matrix is invertible. Okay? Then we will continue from here. Before doing that, remember correlation coefficient between x1 and x2 is defined as covariance x1, x2 divided by standard deviation x1i times standard deviation x2i. Okay, and of course standard deviation is the square root of variance, right? And then like just this is a separate definition. And what was the question? Show that it is identified if covariance is not plus minus 1. So from the previous result, we know that if the determinant of the matrix is not 0, then we have identification beta 0 gamma 0 is something inverse times something, right? We could solve, that is how we solve linear equations. Then the determinant, it depends on the determinant. The determinant is variance x1i, variance x2i minus covariance x1, x2i squared, right? Then I will rewrite the covariance as variance x1i, variance x2i, x2 minus covariance can be written as like correlation. I will define correlation as rho times standard deviation of x1 times standard deviation of x2. You see this? Then standard deviation squared, variance, simply variance 1 times variance 2 minus rho squared, variance of 1 times variance of 2 should not be 0, right? That implies rho squared should not be 1. Pretty simple. Of course, variance is not 0, right? So this is the condition. I deleted it. Right? As you see, the correlation coefficient squared should not be 1. So that means correlation coefficient cannot be plus or minus 1. Okay? That's how we prove this thing. And the mean variable, rewrite the equation. Simple. Clear page. The mean variable, right? yi tilde and x1 tilde, x2 tilde. Okay, I will just I'll show that. Original equation, and if you take expectation of that, you get this. So in the question, I assume that this is 0, but it doesn't need to. Doesn't need to be 0. Or if you take subtraction, then yi tilde, I will cancel out beta 0, x1i tilde, gamma 0, x2i tilde, plus ui tilde. Here, right? Then this is a new regression equation with 2 variables only. Then full rank assumption. To define the full rank assumption, like xi is x tilde I x tilde 2. So uppercase x is 2x1 matrix, 2x1 vector. Then full rank x1 xi prime equals expectation x1i tilde squared, expectation x1i tilde, x2i tilde, so x1i tilde, x2i tilde, x2i tilde squared. The 2x2 matrix looks like this, and we know that expectation of the mean variable square is variance. And this is covariance. We showed why in the previous question, so I believe it is straightforward here. Okay, then for this full rank assumption, for this equation's full rank assumption to be true, delete it again. Then its determinant, it should be invariable. Its determinant should not be 0. That is, the correlation coefficient not equal to 1 or plus 1, right? We get to the same thing. So the full rank assumption is the same thing. We did the last question first, and the exogenate assumption. Let's do the exogenate assumption. I will erase to here. Okay. Still, we have uppercase X like this, and the exogenate assumption is this, which is actually two equations. Expectation x1i tilde ui is 0. Expectation x2 tilde ui equals to 0. Right? We have to show both, and I'm sorry, u tilde here, because we are thinking about this regression equation. So regressors are x1 tilde, x2 tilde, and the disturbance in this equation is u tilde. So exogenate, corresponding exogenate assumption is those things, right? Between these guys and between these guys. And you know, d-mean variable, so covariance. So the covariance assumption is the original assumption we assumed. Okay, so d-meaning does not matter in identifying the slopes, and the intercept. So intercept does not matter, right? Intercept is just very annoying in notation. That's all. Thank you.